Let's review the questions of the productivity module in the same way that we did for process analysis. I will share with you a couple of practice problems, and you'll take a shot at these problems on your own. For that, after I explained the question to you, just pause the video, take some time to wrestle with the question, and then restart the video to hear the rest of the question explained by me. Ready? Alright, here's a Tom and Jerry ice cream store question. Tom and Jerry run an ice cream store, and they have an expensive piece of equipment. Since they're currently running at capacity, they consider buying another piece of the same equipment. However, they consider doing an OEE analysis. They find that not all of the capacity is used productively, and so they use a couple of calculations to figure out what's the real percentage of value add time going on here on their ice cream maker. Alright, here's a good moment for you to pause the video. I'll give you some time, and then I'll show you the solution. Alright, now it's my turn. Let me crunch through the question step by step. The first part of the question asks me, how many good batches of ice cream will there be produced per day? To figure that out, recall that we have basically 12 hours available for production. Of that, 1 hour is lost due to the startup effect. Pardon my bad humor here, this is the funniest I could come up with. So, 11 hours are available for production. 11 hours really means 660 minutes per day. If you think about how long it will take to produce a batch of ice cream, remember a batch of ice cream takes 80 minutes. These 80 minutes are 20 minutes in setup and 60 minutes of actual production. 80 minutes per batch means that we can really make 8 batches per day. Of these, we know that only 3/4 are good and 1/4 is defective. And so that means we're producing 6 good batches per day. This is real value add time. We know that these 6 batches are justifying really 60 minutes per batch of production time, and that gives us 360 minutes of productive time per day. Now, in the last piece of the question, we want to have something brought into the question that talks about every other Friday. So over 2 weeks, we're going to have 13 days times 6 batches, 6 good batches per day times 60 minutes. So over 13 days, we have a total of 4,680 productive value add minutes. How much available time did we have in that 2 weeks? Well, the available time is simply 14 days times 12 hours a day times 60 minutes. That is, according to my calculator, 10,080 minutes. So this here on the very right is the actual value add time, 4,680. Here's the available time, so we can solve for an OEE of 4,680 divided by 10,080, which is roughly 46%. Again, you can now start quantifying the capacity loss effect, for example, of the setup times or of the defects here. And so that gets a nice waterfall chart that makes up for an OEE analysis. The next question is about linking operational measures with financial measures. In particular, we'll have an eye on productivity measures and how they influence the bottom line of the firm. Take a look at the question here. Before you get to the work, let me point out the notion of an ROIC tree. In class, we talked about the KPI tree. KPI stands for Key Performance Indicator, and the computation that I did for the Subway case looked at profits as a pretty obvious key performance indicator that an organization would be interested in. When you do an ROIC tree, you start with the return on invested capital at the root of the tree. This is simply profits divided by invested capital, and then you start the tree by having a profit branch and an invested capital branch. From there, you go as discussed in class. Are you ready? Here you go. The first part of the question is about how many guests we can serve on an evening. Now take a look at the following thought process. The guest will spend a total of 50 minutes in the restaurant. Then 10 minutes are needed to clean up the table. So the total time in the system for the guest and the table, so if you think about the flow time of an order, is 60 minutes. Apply Little's law, I equals R times T, and you know that the restaurant is always full. Always full means that there are always 50 orders in the system, and then R times T, and T is really a quarter of an evening. So if you look at guests per evening, you can solve for R and see 200 guests. You don't really need to do Little's law to find this. You can also think about the intuition that each table is turned 4 times per day. So the table turns are 4 times per day. There are 50 tables, hence there are 200 guests for an evening. To draw the ROIC tree, proceed as follows. Again, start with a profit branch and an invested capital branch. Profits is nothing but revenue minus cost, and revenue is nothing but the revenue per guest times the number of guests per night. The number of guests per night are simply the number of seats that we have available, 50 as we just saw, times the guests per seat, which are driven by the speed with which we turn the seats. This in turn is driven really then by the time that the guest is in the seat or at the table, plus the 10 minutes of cleaning time. On the cost side, we have really multiple brackets of cost. We have some overhead cost, we have some cost for the labor, and we have some variable cost. The variable costs are largely reflected in the food, and those are simply the number of guests times the amount of dollars that we spend per guest on food-related expenses. This gives you in a nutshell how these variables play together, driving the ROIC. I'll now turn to Excel and actually run the numbers. Alright, let's start with the revenue calculations. We begin by looking at the revenue that we get per guest, $20. Then we have the time that the guest is in the seat, plus the cleaning time, which we said right now is 60 minutes. That allows us to turn the table 240 minutes divided by 60 equals to 4 times. Since we have a number of seats equal to 50, we can get revenue, so we can get, number of guests first per night is simply the turns times the number of seats, and that is 200 guests per night. Next, we'll look at our total revenues as simply the 200 guests that we serve times $20 per guest equals to $4,000 revenue per evening. Next, on the cost side, we look at the labor cost first. On the labor cost, we have 20 employees taking home $90 per evening. On the overhead side, that is simple, it's a flat 1,000. And on the variable cost for the food, we have to now look at the guests that we serve, 200, and multiply this with $5.50. So my total cost is simply these three numbers added up. And then I get profits of revenue minus cost equals to $100. Here we have to be very careful because this is the profit per evening. if I want to compute a return on invested capital, returns are typically computed on an annual basis. And so my profits per year are simply 365 times my profits per evening. That gives me then, this is per year, that gives me then my ROIC as the ratio between the profits that I have here and the invested capital that I just squeezed in here. That is 18.25%. Now the reward of all this tricky calculation is that a sensitivity analysis is quite simple. For example, the question alludes to the case that I could shorten the time in the seed to 55 minutes by accelerating the cleaning process. I just type this in, all the numbers recompute, and we see this dramatic increase in ROIC. Now I admit this is based on the assumption that there is really an infinite amount of demand and that we can squeeze these extra customers in, but again, don't be too cautious on the assumptions here, because we're assuming that with unlimited demand and average time, this doesn't really mean that there's always 4 customers being served per seat per night. Some will stay shorter, some stay longer, and as long as there's an infinite demand, we'll always get the extra guests through the system. Anyway, you see now, draw the ROIC tree, compute the ROIC, and then do the sensitivity analysis. Alright, the last question is a line balancing question. You see that there are 6 tasks given to you and a current assignment of tasks to workers. Your job is to balance the line. In the second part of the question, you are supposed to compute the takt time and the target manpower calculation. Now, a word of caution as you start the optimization here to maximize capacity given these 4 workers. As I said in class, there is a way of mathematically formalizing a fancy mathematical optimization problem, but this is really overshooting it. With numbers small as they are here, it's a process of trial and error. You have to just try out different assignment combinations to see if you can further increase the capacity. Good luck! Alright, now let me have a shot here at this problem. Really, we're dealing with a process that consists out of 4 resources, namely the 4 workers. The first resource is just working on task 1, which gives it a processing time of 30 seconds per unit. 25 for the second worker, and then here we combine 3 and 4, so 75 seconds per unit at station 3, and for worker number 4 we have 45 seconds per unit. So we've done this often enough by now in class that we can quickly see that 1 over 75, and this is now units per second, is going to be the bottleneck, and thus this is the capacity of the current line. So this is, again, 1 over 75 times 3,600 seconds in an hour. Now let's assume that tasks are allocated differently. We want to balance the line. And clearly this doesn't look like a really balanced line because there's a big difference between the fellow working here and the fellow working here. So let's see how good we can do. Now imagine the first person here would work on task 1 and task 2. That would give us a 55-second processing time. Then the next person would just work on this one here, 35 seconds for the next one, 40 on the next one, and then 45 for the third step. This would give me an activity time or processing time at the bottleneck of 55 seconds. How did I come up with that solution? Don't ask me. This is a little bit of intuition, a little bit of trial and error. I started with 30, but I doubted that I could get all the way down to a processing time of a bottleneck of 30. Then I tried 30 plus 25 and went from there onward. Could I combine activities so that the processing time at the bottleneck is 55? Yes, I could. Again, this is trial and error as long as you don't learn mathematical programming, which could do this assignment optimally for you. With this in mind, we have a activity time at the bottleneck of 55, and thus a capacity at the bottleneck of 1/5, 55 units per second. The third question is equally tricky. In the third question, you can assume that you can reshuffle these tasks. Now, typically, when you do this, since you're gaining a degree of flexibility, you will be able to squeeze down the processing time at the bottleneck further. However, I couldn't find the combinations of activity times such that the 55 seconds were beaten. Just try it yourself. So maybe you want to combine 30 and 15. It gives you a 45 seconds per unit activity time at the bottleneck. Then you could try, you have 55 up here, that makes it longer. Try it yourself. I couldn't come up with anything faster. So far we have looked at the effect of capacity only. We have maximized capacity. Now we have some information about demand. Demand here is 50 units per hour. Since there are 3,600 seconds in an hour, and we want to have 50 units, we have a 72 second between units takt time. I can quickly compute the labor content of the process as simply the sum of these individual processing time and get a labor content of 175 seconds per unit. My target manpower is then simply these 175 seconds of work divided by the takt time of 72, which is 2.43 people. Round this up and you see that you should hire 3 workers. Now, the last question is going to be tricky. As we go from the target manpower to the actual staffing level, we have to once again tackle the problem of assigning workers to tasks. Let's take a look at this together. Now, here are the processing times. They were, excuse me, I didn't want to log us out here. 30 seconds for the first, 25 seconds for the second, 35, 40, 15 and 30 seconds per unit respectively. Let's first consider the case where we can do the task in any order that we want. Remember, our takt time was 72 seconds. So I want to create bundles of tasks that are very close to 72 seconds. I combine 40 and 30. It gives me 70 seconds, and that worker would just have 2 seconds idle time. Remember, we want to hire n equals 3 workers. That we know by our target manpower calculation. That's the best we can do. Well then, from here onwards it's easy. 15 plus 35 already gives me another 50 seconds. I combine the first, and that gives me, with n equals 3 workers, gives me the process staffing that I need. It's somewhat trickier, unfortunately, if I want to keep the sequence of tasks as they were described in the questions. Again, let's write them all down. And let's remember that once again we are after a takt time of 72. So if I combine the first two, I'm going to get back to my assignment of 55 seconds of a cycle time, or of a processing time at the bottleneck, which we saw previously. That was not enough to get me down to n equals 3. I had n equals to 4. However, if I include all of these 3 tasks together for the first worker, I'm over the 72 seconds takt time. So that means the first worker really has to have these 2 tasks assigned to them. Same logic on the next step. If I combine tasks 3 and 4, I'm over my takt time, and so that doesn't work. And so I have to, unfortunately, hire them and just hire 35 seconds here. Then the next person would be staffed this way, and then the next station this way. So unless I can break up the tasks further and move seconds from one task to the other, unfortunately in that case I will need 4 workers.